Okay, welcome to part 4 of the ASHRAE Standard 90.1-2010. This part involves more areas than we've talked about in the previous parts. First of all, this will have the wrap-up section of HVAC, that is Section 6. But it will also cover water heating, it'll cover power, and it will cover motors. These are, in the standard, these are sections 7, 8, and 9, in addition to the second half of section 6, HVAC. Okay, again, we want to acknowledge support from our sponsors, ARRA, US DOE, and SECO. We'll continue with this part by including here the simultaneous heating and cooling limitations. Any zone controls that have to operate in sequence need to provide heating and cooling energy to the zone that will prevent reheating, recooling, mixing, or simultaneously supplying air that was previously heated or cooled, and any other simultaneous operation that involves heating and cooling of systems to the same zone. Also, hydronic systems need to be controlled to prevent heating, reheating, and recooling of the fluids. Exceptions to this, and there are many, zones for which the volume of air that's reheated or recooled or remixed is no greater than the larger of the following, and they list 4 different categories here that can be reasons for not having to use the zone controls. Also, zones that comply with all of the following: airflow in a dead band less than 20% of the peak supply rate, or outdoor air rate less than ASHRAE Standard 62.1 requirements, or that can be modulated. Mixed airflow rates that are less than 50% of the zone peak supply rate. So again, these are all exempted. Laboratory exhaust systems that comply with a certain regulation that's within the standard, that is Section 6572. And this particular section is in regard to preconditioning of makeup air from laboratory exhaust hoods. Also exempt are zones where at least 75% of the energy for reheat or providing warm air in the mixing systems is provided from a site recovered energy source or a site solar energy source. Now mainly 4-pipe systems are the preferred route for hydronic systems. 3-pipe is ruled out totally because basically a 3-pipe system uses 1 pipe for hot water supply and a 2nd pipe for hot water or cold water supply, but a common pipe for the return. And in that regard, the return pipe more or less neutralizes the heating and cooling you've done in the first place for the hot and cold supplies. So anyway, that's a no-no. 3-pipe hydronic systems are out. 2 pipes are possible. Common 2-pipe distribution system is acceptable if all of the following are met. And that is, first of all, the dead band from one mode to the other is greater than 15 degrees Fahrenheit of the outdoor air temperature. And the controls are designed to allow operation of equal to or more than 4 hours before the changeover occurs. And also, reset controls are provided that allow heating and cooling supply temperatures at changeover point to be less than 30 degrees apart, less than or equal to. Humidification, stipulation on that. And this is a quote from the standard: where humidistatic controls are provided, such controls shall prevent reheating, mixing of hot and cold air streams or other means of simultaneous heating and cooling of the same airstream. And we see another list of exemptions here. Mainly these are based on capacities that might be under a certain amount, like this one right here, less than 80,000 BTUs per hour, capable of unloading to 50%, If you're going to violate the ventilation standard 62.1, of course, that's exempted. And if you have specific humidity levels that are really required, such as in vivariums, museums, surgical suites, certain buildings with refrigerating systems like supermarkets, refrigerated warehouses, ice rinks, and so on, those would be exempt from this. And again, we see this exemption based on solar provided heat. If you have at least 75% of the energy for reheat or warming air before mixing from either a site recovered energy source or the solar, you can exempt from this. Desiccant systems can be exempt also if they have 75% of the heat added, if that's removed by the heat exchanger. Here's a section that limits fan power, and it has actually two different options to it. We show here a little table. It has options number 1 and 2. The first option is where you look at the nameplate horsepower on the fan, and that horsepower has to be less than 0.0011 times the CFM of that fan, if it's a constant volume. If it's a variable volume fan, then that number changes to 0.0015. So it's a little more lenient there, allowing the higher amount of horsepower per CFM, because it's known that that fan will be varying in its speed during the operation of the building. Option number 2 allows a much more detailed look at what's called brake horsepower in lieu of the nameplate horsepower. And the brake horsepower has to be less than CFM times 0.0094 plus a bunch of adjustments. These adjustments can go into a lot of minute details, and I'll try to explain exactly how you would incorporate those. The adjustment's actually made up of a summation of the pressure drop times the CFM across a unit, where the pressure drop is measured in inches of water column for each component, and the CFM is the cubic feet per minute of air crossing through that component. In that equation, we have the summation of the pressure drop times the CFM divided by an efficiency factor 4131. To compute the installed brake horsepower, you use the same equation, but instead of the 4131, you use 6356 times the efficiency of the fan. And in this equation up here, the first one, 4131 already assumes an efficiency of the fan of 0.65. So if your fans are, if your fan motor's more efficient than 0.65, then you get away with a little more leniency on how big your adjustments can be. The next slide will show you what some of those adjustments are for some of the components. For example, if you have a fully ducted return air system, return exhaust air system, and so on, you can add a 1/2 inch water column to that system. If you have MERV filters, you can add different values of pressure drop. For example, MERV 9 through 12 gives you a 1/2 inch pressure drop. MERV 13 through 15 would give you a 0.9 pressure drop. Any other components have specific numbers related to how much air pressure that seems to get dropped during the process of passing through that component. If you have sound attenuation section in the ductwork, you can add another 0.15 inches column pressure drop. Exhaust system serving fume hoods, that gives you an allowance of 0.35. So if you looked in the standards manual, you'd find all the detail related to these, and I don't think I can go into specifics on each one of them here. On the part load fan power limitation, individual variable air volume fans are restricted if they have motors greater than 10 horsepower. Just a note on this footnote that I put on here, that limitation applied to 30 horsepower and above back in 2001, and it applied to 15 horsepower in 2004. Now it applies to even smaller fan motors, 10 horsepower and above. So you can see from this that the standard is becoming more and more stringent as time goes on. Anyway, they have to have a variable speed drive, a VSD, or they have to be vane axial with a variable pitch blade, or they'd have to have other controls that result in a fan motor demand being less than 30% of the design wattage when there's 50% of the design air volume. That's when the static pressure is set, the set point is at 1/3 of the total design static pressure. Exhaust energy recoveries. This is required now. By climate zone, you can see here down on the left column, this table gives you the exhaust air energy recovery requirements, and it's based on the percent of outdoor air at the full design airflow rate. If you go vertically, then you can see that it applies different airflow rates in the different climate zones. So this exhaust air recovery has to recover at least 50% of the energy of the incoming air that's otherwise a load on the ventilation system. The exceptions to this relate to laboratory fume hoods, and there's a particular section that you can look at later possibly that applies to fume hoods that are greater than 5,000 CFM. Other exemptions are systems serving uncooled spaces that are heated to less than 60 degrees, systems that exhaust toxic or flammable paint, corrosive fumes, and so on. Some of the commercial kitchen hoods used for collecting or removing grease vapors and so on. And again, we see where if you have 60% of the outdoor air heating energy provided from site recovered or site solar energy. So this has come up several times now in the exemption list. Anything where you get other energy sources or site recovered, solar recovered energy, that would be an exemption to the system. Systems that operate less than 20 hours a week, those are also exempt. So many exemptions are shown here. The standard does go into a lot more detail than I'm showing on the slide, which applies to almost every slide I'm showing, but that goes without saying that we can't show all the detail that's in print in the manual. This requirement here is for recovering some of the heat that you could use that for service water heating. We're not yet talking about the water heating section of the standard, however. This is still on the HVAC system, and it's saying recover some of your heat if your water heating is used 24 hours a day. If your heat rejection from your HVAC is more than 6 million BTUs per hour, which is about 375 tons of air conditioning, and if your service water heating load is greater than 1 million BTUs per hour. In that case, there is a requirement that you recover some of the heat from your condensing unit into the service water heating. We'll wrap this up with completion requirements. We need to have record drawings for the HVAC. We have to have operating and maintenance manuals. The system has to be balanced, and there has to be a report on that. There is a requirement for system commissioning in some cases. I'll show you the limits on that in a minute. Under the record drawings, though, these have to be supplied to the owner within 90 days after the system's accepted. And that has to include the location and performance data on each piece of equipment. It has to have the general configuration of duct and pipe distribution systems, including their sizes. It has to show terminal air or water design flow rates. Under the manuals, these also have to be provided within 90 days of acceptance. It has to show the equipment size, operating manuals for each piece of equipment, requiring maintenance. The actions have to be clearly identified. And here's one I think is especially important. The name and address of at least one service agency. That really is useful to the building owner in case of equipment failure in the future. HVAC control, system maintenance information. And finally, a complete narrative of how each system's intended to operate. Under systems balancing, that simply has to be done in accordance with the standards that are back in the Appendix E. And the specific requirement on that is you have to have a written report for conditioned spaces that are greater than 5,000 square feet. For commissioning, this is to ensure that the system elements are all operating as designed. And in the plans and specs, the designer has to provide detailed instructions for the commissioning of the projects that are, and this is the limitation here, greater than 50,000 square feet of conditioned area. So anything less than that would not require this sort of system commissioning. The exemption to all of this would be the warehouses and semi-heated spaces. A little section here on alterations. New HVAC equipment used as a replacement does have to comply with the minimum efficiencies that are in the standard. Any new cooling system that serves previously uncooled spaces, that has to comply with Section 6, which is the section we're just summing up right now. Alterations to HVAC shall not decrease the economizer capabilities. So if there's already a economizer cycle in the system, you cannot decrease its capabilities. The new and replacement ductwork, of course, has to comply to those particular sections that we covered a few minutes ago on insulation and duct leakage. Here are the exceptions to the mechanical alterations. If the equipment is simply being repaired and there's no increase in the energy consumption, if the compliance simply requires such an extensive revision that you can't get at the equipment, that's also going to be exempted. Changing of refrigerant only, that's exempted. Just relocating equipment is exempted. Also, on ducting and piping, if you cannot get at it, it's exempt. So those are all out of the requirements. So that concludes the HVAC portion of the standard. Now we will look into sections 7, 8, and 10. These are the service water heating, first of all, the power limitations, and then 10 will be on other equipment, and that's mainly motors. On the service water heating compliance, we have this familiar diagram to look at again, going from mandatory provisions down through prescriptive requirements and then on to compliance, or taking the alternative route of going through the energy cost budget. I haven't said a lot about this so far, so I'll say it now. Anything that cannot be done with the prescriptive path, that is, if you cannot possibly meet the requirements of the standard, the option is always open to then go back and use this energy cost budget route and therefore meet compliance. Again, even though the prescriptive is not met. Mandatory, on the other hand, does have to be met. So that one's an item that has to be done for sure. On the service water heating equipment efficiency, we have a table in here, 7.8. If the equipment's not in the table, it literally has no minimum performance requirement. What we'll be looking at in table 7.8 will show the water heater efficiency requirements for the heater itself, and it also shows standby losses. They denote those as SL. So the exception, however, to the requirements is if your water heater and water supply boiler is greater than 140 gallons, that storage system does not have to meet the standby losses. If this tank surface is thermally insulated to R12.5 and a standing pilot light's not installed, and a gas or oil-fired water heater having a flue damper or fan-assisted combustion. So any of those would comply with the exception here. This is the table. This is a partial segment of the table. That table does go on rather in lengthy form for about 2 pages. But this shows all the different types of equipment, what size they are based on BTUs per hour, possibly a storage capacity size, as you see here, 20 gallons or more. And then over here we have the equation for the actual performance requirement. And to interpret this for you, look at the first line there. It says 0.67 minus 0.0019 times V. That's the efficiency requirement of the heater itself. And they follow that with the symbol EF. That means the equipment efficiency factor, I'm sorry. If you see an SL, it means the standby loss. So what we have on the remaining hot water heaters here is we have a minimum efficiency factor. This one says 80%. And then the standby loss is separate from that. It's Q over 800, Q being the BTUs per hour of rated heating capacity of the heater, plus 110 times the square root of V. Now V is the volume in gallons of the storage tank. And that is the standby loss. That's in BTUs per hour. So that's the second limitation of the capacity and the efficiency of the water heater. On piping insulation for hot water, basically it's the same as that for the HVAC. So back in Section 6, we actually looked at a table that had the R values for these pipe insulation factors. And it's specifically now for hot water systems, though, that is service water heating systems. If you have a non-recirculating storage system, then the first 8 feet of the outlet piping are what's required to be insulated. Also, if, insulate the pipe between the storage tank and a heat trap. I'm going to show you a heat trap here in a second. Or you could have externally heated pipes, heat trace, or impedance heating would be required there. Many systems are designed with circulating pumps on them, and basically this has a restriction on limiting the operation of that recirculator pump to a period from the start of the heating cycle to a maximum of 5 minutes after the end of the heating cycle. That's to make sure you're not just simply pumping around a lot of water, losing heat when the water demand's not in use at all. Now here's the definition of a heat trap. A heat trap has to prevent the internal convection currents from the hot water heater from going up through the pipe and losing the heat through the piping system throughout the building. So any non-recirculating system has to have a heat trap on both the inlet and the outlet piping, and that should be as close as practical to the storage tank, unless that storage tank has some kind of an internal heat trap to it. The arrangement of a heat trap is this. The water has to basically go through a reversal to prevent the convection currents from occurring and going up through the building. The example shown here on the left shows the pipe coming out of the hot water heater and going up, then reversing totally backwards, and then making another U-turn and going back up through the building. And this will prevent the hot water convection currents from going up through the pipe, losing their heat and coming back down again. The second example is shown over here at the right, where the pipe comes out and just simply makes a 360-degree loop turn before going in the wall and up through the building. So you can have various forms of heat traps. And as I mentioned, some of these could be internal to the water tank, and those would be provided by the manufacturer. This is the limitation on the standby loss, and that equation is 13.3 times this PMD. That's the probable maximum demand of water per hour. That's gallons per hour, plus a constant, 400, and divide that by N. N is the percentage of the year, fraction of the year literally, when the outdoor daily mean temperature is above 64.9 degrees Fahrenheit. That's pretty much saying that's the fraction of the year in which the days are more or less in a summertime condition. Not the cold days, but the hotter days. And I do want to note here that the parameter N is not found in the climatic data tables in Appendix D of the standard. They do have a lot of other information there, but this one in particular is not shown there. So you would have to get this value in from some other independent weather source probably. And that, in a short time, concluded the service water heating. And even shorter will be the power section. That's Section 8. This section is all mandatory. There's no prescriptive or alternative paths available to you. It's going to deal with voltage drop. It's going to talk about automatic receptacle shutoff controls, and it's got a portion on completion requirements. As far as the transformers involved, this is the power transformer requirement here in the efficiencies, and basically they're showing the kVA size of single-phase transformers and also three-phase transformers. Beside that, look up the size of your transformer, and right beside that you'll see the efficiency number that's required. On the voltage drop, there are two types of conductors that are restricted. First of all, the feeder conductors. These are the wires that run between the service entrance and the branch circuit breaker box. And that's restricted to a 2% maximum voltage drop. The other requirement is on the branch circuit conductors. That's run from the circuit breaker to the load or the outlet. And the allowable limit there is actually 3% on the voltage drop. And pretty much that's all the requirement on the efficiencies. Now on the controls, there are no limitations on what we call receptacles in the building as far as their sizes go or their wattage and so on. A lot of that's controlled by the Department of Energy, that is on computer efficiencies and so on, refrigerators, fax machines and so on. But what ASHRAE requires is an automatic control on the receptacle outlet. And what it says is at least 50% of all 125 volt, 15 amp or 20 amp receptacles included in these spaces, that is private offices, open offices, and computer rooms, shall be controlled by an automatic device that has a scheduled cutoff time. In other words, it has a time of day operating programmable control device and or an occupant sensor that actually will turn off the receptacles within 30 minutes of the room being vacated. So even though the amount of plug load, some people call it plug load, is not regulated, the time that it's on is regulated by the ASHRAE standard. There are exceptions to this. That is receptacles for equipment that has 24-hour operation. That seems quite logical. And spaces where the automatic shutoff would endanger life safety or security. And of course that issue is throughout. Nothing in the standard is supposed to endanger life safety or security. This has a submittal requirement also. The owner gets the information about the building's electrical system. Rather than within 90 days of completion, this one's within 30 days. And the manuals that are to be provided are very similar to those required for the HVAC submittals. And that would conclude Section 8. Section 10 is also all mandatory, no prescriptive or alternative paths here. And this relates mainly to electric motors. The electric motors shall comply with the Energy Policy Act of 1992, and that's summarized here in this table. In the book, it's Table 10.8a. Motors that are not within the scope of the EPA have no requirements in this section at all. So in the table, what we're looking at is the size of the motor in horsepower, and then just beside that, depending on whether it's an open motor or enclosed motor and how many poles it has, you'll find out the motor efficiency. And those efficiencies run basically between 90 and 95%, somewhere in that scale. This concludes Part 4 on the mechanical systems that included HVAC, surface water heating, motors, and other equipment. The only other remaining section now will be Section 9, and that will be covered in Part 5 of this series. Thank you very much.